Okay, let's look at number 14. So 14 wants to know which of these would have, at least have one 90-degree bond angle. Now you notice I'm saying draw the Lewis structures, but as with all of these, the test may not ask you to do that. So you always need to do that, whether they ask for the shape, as in is it trigonal planar or something like that, or what is the bond angle, or is it polar, you got to draw the Lewis structure. So we're going to do the first one together, and then I'll just sort of list the others so you don't have to watch this process over and over again. So let's start with A. We know that bromine is going to go in the middle, and the fluorines are going to go on the outside. To count the valence electrons, we know that each bromine is going to contribute 1, 2, 3, 4, 5, 6, 7 electrons. Each fluorine is also going to contribute 7 electrons. So that's 7 times 4, we're talking 28 electrons. Then I'm going to go around the outside. And once I've gone around the outside, I will have used up a total of 24 electrons. So that gives me a couple more to put on. So I've got 20, that gets me to 26, and 2 more on the bromine gets me to 28. So start on the outside, go to the inside, and we're set. Now let's see if this particular one gives up a 90-degree bond angle. To do that, we've got to transfer this to a shape. So you notice that there are actually 1, 2, 3, 4, 5 directions coming from the bromine. That main shape is going to be trigonal bipyramidal, so kind of like this. There's trigonal bipyramidal with 5 directions. And you'll notice that a trigonal bipyramidal does have a 90-degree bond angle. From the top to the side is a 90-degree bond angle. It also has a 120-degree bond angle. So it may be that A is our correct answer. And I'm pretty confident in that, so I may circle and move on. But you should always draw the Lewis structures of all the others. So here are the Lewis structures of the others drawn. And I did start around the outside and then go to the inside. So you can draw them and confirm that you got this too. But you'll notice PF3B has 4 directions. 1, 2, 3, 4. Oops, I forgot to draw the bond there. But there's 4 directions, so it would be tetrahedral. It would not look like a T. It would have bond angles of 109.5, so that's not the correct answer. If we went to CF4, this is what it would look like if we did around the outside and then the inside. Again, 1, 2, 3, 4 directions, also tetrahedral, also 109.5. Then if we do the same thing with BF4 minus, remember to add in that extra 1 electron, you get 1, 2, 3, 4 directions. It also is tetrahedral. And lastly, CO2 only has 2 directions. This one we had to share in order to help the carbon out a little bit. But it only has 2 directions, so it really would be linear and the bond angles would be 180 degrees. So the correct answer is A. Number 15. Which of the following would be a non-polar molecule? Now they're talking about the molecule, not just the bond, so we do need to draw Lewis structures. And again, the test is unlikely to tell us this, that we need to draw Lewis structures. You just need to know that if they ever ask the shape, the bond angle, or whether the molecule is polar or not, you always got to draw the Lewis structure. Let's do the first one together, and then I'll just draw the other ones. So let's see. I'm going to put the Se, the selenium in the middle, and the 2 sulfurs on the outside. Selenium is going to have, let's see, where's selenium? There it is. So it's going to have 1, 2, 3, 4, 5, 6 valence electrons. Each sulfur is going to have 1, 2, 3, 4, 5, 6 valence electrons. So all 3 are going to offer 6 valence electrons. That's a total of 18, and there's no charge for me to worry about. All right, so I know I have 18 now. I'm going to write that down because I'll forget it. I'm going to start around the outside, and then I'll go to the inside. So we've already used 16. There's 17, 18. I have 1 lone pair. Now you notice I can't stop here. Do you see which atom doesn't have a satisfied octet? Definitely the selenium. The selenium only has 2 electrons here, 2 there, and 2 there. That's 6. So we've got to share. So that means we need to get rid of 2 of these. I'm going to cross these out and drop them down and make a double bond. And now the selenium has 2, 4, 6, 8. And this sulfur has 2, 4, 6, 8. This sulfur has 2, 4, 6, 8. There we go. It's ready to go. Now, if we're going to figure out if it's a polar or a non-polar molecule, then at this point we need to draw a more accurate shape. And you remember that there are 3 directions coming from the selenium. which means the main shape that it's going to take on is something that's more like a trigonal planar geometry, where the bond angles are 120. This one on top is actually a lone pair, and you remember that nobody's pulling on a lone pair. So it's really only the sulfur where we have dipoles. These dipoles are not in opposite directions, so there is going to be a net dipole. So this is going to be a polar molecule, because there is a net dipole. Now let's draw all the other Lewis structures, and we'll make the same arguments for that. Alright, so I haven't drawn them all here, but I did draw B, and I drew C here. So let's walk through the argument about, let's try to figure out if B is polar or nonpolar. We're looking for something nonpolar, but so I've drawn it out here. And remember, I did start around the outside, and then I went to the inside and I had a lone pair here. On the XE, there's 1, 2, 3, 4, 5 directions, which means the main shape is going to be trigonal bipyramidal. So something like, I'm going to draw it over here so we can see it a little bit better. It's going to be something that looks like this. Okay? Now, where's the lone pair? Well, the lone pair, you remember, is always along the belt line, so it's right here. And then after that, let's consider, we don't really know where these atoms are. But let's say optimally that this is a sulfur and these are iodines over here. Well, the sulfur dipoles may cancel each other, but the iodines certainly aren't going to. And so this molecule is going to end up polar. So there's going to be a net dipole sort of to the right there. If we do the same argument for carbon dioxide, I think this is going to be our nonpolar molecule. And so the answer is going to turn out to be C. Because remember that what's happening here is I ended up short of electrons and they had to share electrons down to get to the CO2. Because there are two directions, one direction going this way and two directions going that way, this really is a linear molecule. And because it's linear, when we go in to draw the dipoles, the oxygen's going to pull electrons this way, and the oxygen's going to pull electrons that way, and therefore they will offset those dipoles, and so this will be a non-polar molecule. So I think C turns out to be the correct answer. Now I would suggest you, because remember we're studying, draw these other two and convince yourself. I think they're probably going to turn out to be polar since they weren't the answer. But draw them and see if that turns out to be true. Alright, on to 16. They want to know which of these would have linear molecular geometry. And remember, molecular geometry means a sub-geometry, not a main shape. But it shouldn't make too big of a difference either way. So which of the following molecules is polar? Now, the fact that they told us that all of the molecules have a linear molecular geometry might mean this is the one case where maybe we don't have to draw out all the Lewis structures because they're telling us the shape of it. Now, I would always advocate drawing them out, but think about this. If they're saying that they're all linear, so I don't know if these are double bonds or triple bonds or whatever, but the one thing we know is they're linear. So if we look at this first case, there's a pull towards the nitrogen because nitrogen is more electronegative than carbon. Agreed? Sulfur is, it's hard to tell, but I suspect it's more electronegative than carbon as well. But the odds that these two are going to pull the same is not very good because nitrogen and sulfur are not the same atoms. Matter of fact, sulfur is closer to fluorine, so I might suggest that that one's going to pull harder and that the nitrogen is going to pull a little bit less hard. In any case, they're not going to be the same pull, so definitely that is going to be a polar molecule. So I think A might be the answer. But let's see why B isn't the correct answer. So I don't know if these are double or triple bonds or whatever. Because they told us the geometry, maybe we don't have to draw the Lewis structure. It actually turns out, by the way, that when you're doing these, if you go around the outside first, you're going to need to share. And so that's what it's really going to look like. But you notice that the sulfur is more electronegative than the carbon. So there's going to be a dipole pulled this way, and the electrons are going to be pulled that way. But because the sulfurs are the same electronegativity, that pull is going to be the same. And because it's linear, they're both going to offset. That's a non-polar molecule. If we look at C, well, that's just two oxygen atoms. Of course it's linear. Now, there may be a double bond or triple bond, but it doesn't make a difference. The fact is that when they pull, they both pull sort of with the same strength because they're the same atom. So it's also nonpolar. So definitely A is going to be the correct answer. Now I do want to caution you, because if there's anything the students do wrong in this test, it's not drawing Lewis structures. And you really should draw all these out. It's only the fact that they told me what the geometry was that keeps me from having to draw them out. Because if any of these was bent, it would change what you have to do to figure out if it's polar or not. So always draw the Lewis structures out. On to number 17. What is the molecular shape of NO2-? Again, we're looking for a subshape. Again, the test is not going to tell us to draw the Lewis structure, but they want to know the shape. There's no other way to do it. Remember, the pitfall here is some people think, well, you know what? There's 2 oxygens, so this thing's got to be linear. But there might be a lone pair. We don't really know. We've got to figure it out. So I'm going to say that the nitrogen's in the middle, and let's add up the valence electrons. Well, each oxygen is going to contribute 6, and the nitrogen is going to contribute 5. Now you notice if we add that up, we get 12 plus 5, we're going to get 17, which is an odd number, so that's not really working out. But they said it was negatively charged, so we've got to add one more, and we're going to get 18. Now we go around the outside, and you'll notice we've used 16 at this point. We have 2 left, so we come to the middle, and then we're done. Although we're not done, because which of these 3 atoms is not happy? Well, clearly it's the nitrogen. It has 2, 4, 6 electrons. We've got to do something about that. So we're going to take these 2, and we're going to drop them down and make a double bond. That'll let us have a nitrogen that has 2, 4, 6, 8 electrons. It's good to go. And the oxygen still has 2, 4, 6, 8. It's good to go. And of course this one over here is fine as well. Alright, so we're doing pretty good. So we've drawn the Lewis structure, and now we get to figure out what the molecular shape is, which is the subshape. Now, you'll notice that there are 3 directions coming from the nitrogen, which means its main shape is without doubt going to be trigonal planar. The bond angles are going to be 120 degrees. But one of these is a lone pair. Say this one right here is the lone pair. This is the nitrogen. These are the oxygens. And so the subshape is going to be bent. So C turns out to be the correct answer. On to number 18. They want to know what the electronic geometry and molecular geometry, so they want both the main shape and the subshape around the oxygen. And the thing is that what we're trying to show here is in a larger molecule, there's going to be shape around each central atom. And so they only want to know the shape around the oxygen. Well, if you count how many electron groups or directions there are from the oxygen, there's 1 in this bond, 2 in the other bond, 3 in that lone pair, and 4 there. There's 4 general directions. And we know that the shape that 4 directions takes is tetrahedral. So the main shape is going to be tetrahedral. And actually, that might already give us the answer, because none of the rest of them have tetrahedral as the main shape. Now, what is the subshape? Well, 2 of these things are lone pairs, right? So if I redraw it with 2 of them as lone pairs in the exact same geometry, there we go, then you'll notice the bond angles are still 109.5, but what's left is something that looks bent. So the answer is tetrahedral bent. B is the correct answer. Lastly, number 19. We want to know what the bond angles would be in this molecule. Okay, so again, got to draw the Lewis structure. They didn't tell us to, but if they want to know the bond angles or they want to know the shape name, we got to draw bond angles. If they want to know if it's polar, we got to draw bond angles. So let's figure this out. So, you know, when you're talking about 3 elements and you're trying to decide which one goes in the middle, you remember the least electronegative does not go in the middle, or it goes in the middle. So fluorine being the most electronegative definitely is not going to go in the middle. It's going to go on the outside. But between nitrogen and oxygen, you notice nitrogen is less electronegative than oxygen. So I'm going to put the N in the middle. And very often when there's only 3 elements, they do write them in the order that they should go. Okay, now we got to count up our valence electrons. Well, each fluorine is contributing 7, the oxygen is contributing 6, and the nitrogen is contributing 5. Let's see, that's 13 plus 5, we get a total of 18. Is that right? If I add it the other way, 6 and 5 is 11, 11 plus 7 is 18. Yes, I do have 18 valence electrons, which is good because it's an even number. Now we go around the outside with our electrons, like that, and you notice we've used 16 already. 2, 4, 6, 8, 10, 12, 14, 16. We've used 16. Okay, now we come back, we have 2 more, we go like this, draw a lone pair, but we can't stop here because remember the nitrogen is not happy, it has 2, 4, 6, so we've got to share. So I'm going to take these 2 and drop them down like that. Alright, now let's see where we're at as far as shape goes. Well, just because we drew it linear, remember that does not mean it's linear. It has 3 directions coming from the nitrogen. 1, 2, 3, which means its main shape is going to be something that looks trigonal planar, where this is the N, that's the F, that's the O, maybe I'll draw the double bond in there, and this thing is a lone pair. The bond angles are going to be 120 around this thing, so C is the correct answer.